propulsion. So let's say the rocket, along with its initial mass of the fuel. So when it gets started off, right at the very beginning, let's say the combined rocket plus fuel has a mass equal to m. So the mass is m, capital M, and the velocity is, well, it is just taken off. No, initial velocity is v. Not the initial, but at any point, let's see. Not the initial, at any point, it has a mass m. That's the mass of the rocket along with the fuel, and it has a certain velocity v. So this v is actually a function of time, and so is the mass. These are functions of time. Because of what? Because the fuel is burning. And the purpose of that is what? Why do you make? Why do you actually want to make this combustion engine and burn the fuel? So that what happens? Exactly. So that the huge amount of fuel that you burn that presses on the surface of the earth, that in turn provides an upthrust, which is just like from third law the reaction force on the rocket. Right? So by manipulating the amount of fuel that you burn via this combustion engine of the rocket, you can actually manipulate the force on the rocket. So that's the purpose. So now, let's say after a time delta t, certain small amount of time, the mass of fuel that is burned is delta m. So after a time delta t, mass of fuel is burned or exhausted, I would say, is delta m. And the velocity of the exhaust and this is with respect to the rocket is Ve. Please understand this here. After a time delta t has expired, right? The mass of the fuel that has been exhausted is delta m. And the velocity of the exhausted fuel with respect to the rocket, remember the rocket is already traveling, it has got a velocity. With respect to the rocket it's Ve. So with respect to the earth, it would be how much? Because it's a relative velocity thing. Do you get the situation? Imagine the situation, the rocket is traveling up with a velocity v. That's the instantaneous velocity of the rocket fuel system. And furthermore, it has exhausted the fuel with velocity ve with respect to the rocket. So with respect to the earth is like the stationary reference frame. So with respect to the earth, it would be v plus v. It's actually v minus of minus v because it's downwards. So the resultant with respect to the earth is v plus v. Why is that important? Because we'll be doing conservation of momentum from a particular reference frame. That's why you need to take care of the right velocities. If you're applying partially, you are doing it from the frame of the earth, and the other half you are doing it from the frame of the rocket, it would be incorrect, obviously. So we will do it from the reference frame of the earth, which is stationary. That's why this is important to understand that Ve is with respect to the traveling rocket, but V plus V is with respect to the stationary rocket. Okay, so what is the initial momentum then? It's just the mass times the velocity. It's just m times after time t, delta t has elapsed. After delta t has elapsed, I'll call that t final. What is that t final?
Minus delta m.
Huh? That would
Minus delta.
No.
minus delta m.
We are conserving the momentum of the rocket. Okay. So what is the mass of the rocket after delta m has burnt out?
M minus delta.
M minus delta m. It is not delta m. Because if it's only delta m, then you are actually taking the fuel into account. You need to conserve that of the rocket. So it's m minus delta m times
B plus
v
Minus
plus delta. Let me check on, have a check on this as well. How about the signs? Yeah, it's v plus delta. Yeah, so that would be that of the rocket. And then you have the fuel also exhausted. So this is m minus delta m is the instantaneous mass of the rocket. Rocket along with the fuel that is not burned times the velocity after the fuel is exhausted. So it's v plus delta. And now you also have to take into account the mass of the burned fuel or the momentum of the burned fuel. It's delta m times v plus ve. So that's the v plus ve with respect to the earth. So this is that of the exhausted fuel. So whatever initial momentum you had, m times v to start with, that has kind of been split up now that your fuel is burning into partially into the mass of the rocket along with the unburned fuel, that's the first part, and the exhausted fuel. And obviously from conservation of momentum, we know that this has to be equated to this. Pi equal to EL. That should happen at any stage of its trajectory, this should hold. So equate that m times g is equal to m minus delta m times v plus delta v plus delta m times v plus okay. So I'll just you can just do the algebra and you will see that you get m times delta v minus delta m times delta v plus delta m times v. You do the calculation and see this. Now we have an argument here to make. See, delta n and delta v both are very small quantities. So you are basically, as compared to what? As compared to the delta v's and the delta m sitting towards the left and the right, this quantity is furthermore an order of magnitude less. Why is that? Because you are taking the product of two further small quantities. It's like if you compare 0.001 to 0.001 square, which one is small?
0.001
One
square.
square, right? So if you multiply quantities which are infinitesimal, doesn't matter if they are quantities like mass and velocity, if they are tending to a zero, then the product of those could be neglected as compared to, so it's like of the order of delta x square, and these are delta x kind of quantities. So the argument here is we'll neglect this. Neglect this one. Okay, so the resultant will give you that delta p. Now if you take the should have actually, so this is basically the delta P, not Pi equal to Pn. So this is basically the change delta P. So delta P is Pf minus Pi. Okay, it's Pf minus Pi. So this is basically delta P. The idea of finding out delta P is such that I can find out the force. Because remember, force is delta P over delta T. The rate of change of momentum is the force. So by finding out the change in the momentum of the rocket and divide that by this instantaneous time delta T, I should be able to figure out the force on the rocket. Okay, so delta P will just be m times delta V plus delta m times V, because this has been dropped out. So it's just this plus this which I have. So now as your delta T will tend to 0, you can write down delta P over delta T to be, so it's like taking the limit. So this will just be dp/dt. Straightforward calculus. So now divide delta P over delta T. That is, do dp/dt directly. So dp/dt equal to m times dv/dt plus
dm
ve dm dt. So this blocked equation is basically an equation which connects, you see, for the first time there is a rate of change of mass involved. The mass is changing with time. For all previous examples that we have been dealing with,
mass is
mass
constant.
was constant. So this term never appeared. And you always had, if you forget about this, is m times dv/dt, which is basically mass times acceleration. Okay. So this dp/dt and we know that from the second law. So maybe where can I do this? Maybe I can do this here. So from the second law, we have dp/dt equals the force. Okay. So that would mean that m dv/dt, just follow from that equation, m dv/dt equals external force minus plus ve times dm dt.
So it should be minus for that.
So this basically, this on the left hand side is the net force acting on the rocket. Now what is this external force? This external force is basically the gravity force acting on the rocket. And this is the net force on the rocket because the fuel is burning. See, if nothing had been burning, then dm/dt would have been 0. Then the external force of gravity should have just been equal to m dp/dt. And dp/dt is nothing but g, because it's a gravity field, so it's m times g. Because it's a dynamic system, because the mass is changing, that's why that's the net force acting on the rocket. So you see the difference now when you include changing mass, the rocket propulsion being the most common and the most relevant example. This is how the equations get changed. Okay. Now you can also find likewise, if the external force field is 0. Suppose this external force field is 0 now. That would be a situation when it has escaped the gravity field of the earth, then the external force field would be 0. So if that would be the situation, then you can neglect this term. So suppose now let's say if external is 0, then you would just say that m dv dt would be equal to VE df dt. Right? So now m dv dt would be the net force now in the absence of anything external. Now df dt is a quantity which is what? In sign, would it be positive or negative? It would be negative. Why is it negative? Because the mass is burning. It's decreasing over time. Also, VE as a quantity is negative. Because with respect to the rocket, V is what? It's with respect to the rocket, remember? So it has a negative direction. So a negative times a negative gives you a positive one. So the thrust on the rocket is always positive. So even when it escapes the gravity field of the earth, that's when the situation if external equals 0. Then also it will continue to maintain an upthrust and keep on moving forward. So that was the idea of pointing to this special case. When it escapes the gravity field of the earth, you no longer take this term into account, and then this is the net upthrust on the rocket. So let me write it down as upthrust. Okay, and finally to complete this would be your job to find out how the velocity changes with mass. So all these relate velocity and masses to time. So now take it as a homework example again, homework problem. Find out how the velocity changes as a function of mass. I'll tell you the final answer. So the V is equal to V naught. V naught is like the initial velocity. Thus, logarithm of m over n naught. Sorry, there is the V easily. You see in this equation there is no time involved. So V, this is the initial velocity with which the system has taken off. M naught is the initial mass of the system. If you eliminate time, you should be able to recover this equation, which is basically an equation of motion for the rocket equivalent. So try that out. Given these formulations, try out that particular relationship. Let me quickly take your attendance.